Nathan Putch. I go to St. John the Evangelist School, and I'm in the 8th grade. Prepare to be blown away. I was interested in doing a wind turbine project, so I started to do some research, and I found these maps. This map shows where the wind turbines are located in the United States, and most of them are located in the central part of the United States. But I also noticed that there are hardly any in the southeast. So to answer why this happens, and I looked at an average wind speed map of the United States, and it shows that the central part of the United States average wind speed is from 7 to 10 miles an hour, and the southeast is from 4 to 5 miles an hour, which is quite a bit less from the central United States. So I concluded that the current wind turbine design does not work efficient at low wind speeds. So I wanted to see if a wind turbine could be designed to work more efficient at low wind speeds. So as I continued my research, I found that a wind turbine blade is very similar to a airplane wing, and that is because they are shaped the same. The top is curved while the bottom is flat, and this shape creates the lift because the air must go faster over the curve of the top, and this creates a low pressure zone, which results in the force called lift. And an airplane will increase its angle of attack at low wind speed, or when it's flying slow, so it will still create the same amount of lift. And it can do this because as it increases the angle of attack, the curve over the top of the wing also increases, so the air must go even faster over the top, and this results in even more lift. So knowing what I know about an airplane wing, I wanted to apply that same idea of increasing the angle of attack to the wind turbine. And so I formed the hypothesis that increasing the pitch of the blades will increase the wattage produced at low wind speeds. So the materials I used were the wind turbine, the 3 blades, the generator, which is in the back here, the digital multimeter, the wires to complete the circuit, the 1.5 volt light bulb, the anemometer to record the wind speeds, and a 50 centimeter fan to create the wind, and a wind tunnel to focus the wind, because without the wind tunnel, the fan will create a type of wind that vortexes away from the wind turbine, and this is not like the natural wind outside. So the wind tunnel helps focus the wind. And I also use duct tape and a 100 treble out light to see in the wind tunnel. My independent variables were changing the pitch of the blades, which I did by moving the fasteners, and the other thing I changed was the wind speeds, and I did that by moving the position of where the wind turbine was in the wind tunnel. And the procedure I used consists of 8 steps. The first was to connect the wind turbine blades to the shaft, and then to the generator, and then finally to the tower. Then I completed a circuit with the wires, the 1.5 volt light bulb, and a generator. And then I built the wind tunnel tested the wind at different positions in the wind tunnel to find where it is 2, 4, 6, and 8 miles an hour. Then I measured the volts and the amps and took 5 measurements of each at 2 miles an hour, and then I changed the blade pitches from 10, 20, 30, 40, and 50, and then I did all those steps again at the wind speeds of 2, 4, 6, and 8 miles an hour. Then I calculated the wattage by multiplying the volts and the amps. So I recorded over 200 observations and then summarized them into these 3 graphs. This graph here shows the volts generated, which is the actual amount of electric particles. And the graph shows the volts by the blade pitches of 10, 20, 30, 40, and 50 degrees. And then it shows the wind speeds of first 2, 4, 6, and then finally 8 miles an hour. And as the wind speed increased, the amount of volts also increased. And what also happened was that up to a certain point, as the blade pitch was increased, more volts were increased. So for the low wind speeds, it was 40. So it would go up to 40, keep increasing the amount of volts, and then it would drop drastically after 40 degrees. And this was the occurrence for the blade pitches of 2, 4, 6, 2, 4, and 6, which were the low wind speeds. And then at 8 miles an hour, though, that point was 30 degrees, and so it went up to 30 degrees and then decreased after that. And then here it shows the amps generated, and that is the flow rate of the electricity, or also known as the pressure. And it is shown by the amps and the blade pitches of, once again, 10, 20, 30, 40, and 50. And the same trend held true here, once again. And so as the wind speeds went up, more amps were created, and then up to a certain point, as the blade pitches were increased, more amps were created. And the point for the low wind speeds was once again 40, and then at the higher wind speed of 8, it was 30. Then I multiplied the amps and the volts for each blade pitch and wind speed to get the watts, which are the amount of work that the electricity can do. And for the third time, the same trends were supported. And so as the wind speeds were increased, more watts were created, and up to a certain point, more watts were created as the blade pitches were increased. In conclusion, the hypothesis was supported that increasing the blade pitch up to 40 degrees will produce more watts at low wind speeds. And this is likely to happen because as the pitch was increased, more lift was created and up to a certain point. And so as the pitch was increased, the curve was also increased, and this created more lift and resulted in more watts. But at that point, the airflow was disrupted and resulted in less lift. And this was because at higher wind speeds, there are more air particles there, and they will collect easier, and they can get caught up with each other, and this will result in less lift. But going back to my purpose, to create a wind turbine to work more efficiently at low wind speeds, this information would support that idea of increasing the pitch in areas such as the southeast that have low wind speeds of 6 miles per hour or lower. And to improve my study, I would test at higher wind speeds to see if the trends would continue at wind speeds of 10, 20, or even 30 miles an hour. But I would have to obtain a larger fan that could produce these winds, because the fan I used was not able to do this. And I would also test the different shapes of the blades. But I had a lot of fun doing this experiment, and I would enjoy to continue this study, and I would be glad to answer any of the questions you have.